Welcome to Structural Analysis 2 video series, unit number 5th, Finite Difference Method. Lecture outline: numerical on non-prismatic simply supported beam. So here the numerical on non-prismatic simply supported beam is given. Non-prismatic beam means beam having a varying section. Now numerical statement as follows: using finite difference method, determine the deflection under the concentrated load 25 kilonewton acting at the center of a simply supported beam of a span L. Take EI constant and use 5 nodes. Now in the figure, beam AB is given, which is supported on the simply supported support at A and B, and whose section is varying along the length, and 25 kilometer point load is acting at the center. Length of a beam is 6 meter, so we need a 5 nodes. That means we have to divide the beam into the 4 part. So let's see the solution. uh, the no this AB beam is divided into 4 part, so interval h is equal to L by 4. So total length is of 6 meter. So 6 divided by 4, it become 1.5 meter. So each interval between the node, let us assign node 1, then 2 and 3, 4 and 5. So there are 5 nodes, and each node is at interval of 1.5 meter. So node 1 is at right support, node 5 is at left support, and h is equal to 1.5 meter. Now let find out the reactions at A and B. Now the 25 kilonewton point load is acting at the center. So reaction will be half of that, 25 divided by 2. It become 12.5 kilonewton at A and 12.5 kilonewton at B support or right support. So now the point load is at the mid span, so we can find out the bending moment as PL by 4 or WL by 4. So by putting we will get W is or P is 25 into length is 6 divided by 4. We have 37.55 as a moment at the midspan. So this is a moment here, 37.55. Now there are node on either side. If this moment is 37.55, here the load or beam is symmetrical. If you will see, this beam is symmetrical, so the whatever the moment to the node 2 and node 4, they will be same or due to the symmetry. So 37.55 55 divided by 2, it become 18.75. so at both side it will be 18.75 moment, which is half of this 37.55, because the beam is symmetrical on both side. That's why. So the uh, we having a now bending moment diagram and value of a moment at the node 3 and 2 and 4, and the ends are simply supported, so bending moment will be a 0 at A and B. Now draw the M by EI diagram. Now here the section is varying, so that's why the diagram is shown in a varying fashion. And now here we must note down that the now for the uh, if this was node 2, 1, 2, 3 and 4 and 5. So at node 3 the moment of inertia is 2I. So node 3 moment of inertia 2I. Now at node 2 and for node 4, they are symmetrical, so moment of inertia will be same. So at node 2 the section changing the moment of inertia, so we have to take average of either side span. So here it is I, and on right side it is 2I, so we have to take I plus 2I divided by 2, average of both, it become 1.5I. So moment of inertia at 2 and 4, where the beam changing the section, it will be average. So I2 is equal to I4 is equal to I plus 2I divided by 2, it become 1.5I. So at here and for this one, I2 and I4, the moment of inertia, we have to consider 1.5I, and here it will be a 2I, because at the center it is 2I. So this thing we should be put at a time of calculation, or must consider at a time of calculation. Now apply the initial boundary condition. Now as node 1 and node 5 are simply supported, so the y1 is equal to y5 is equal to 0. So here, and also it is symmetrical, so whatever deflection at y2 is equal to y4 due to the symmetry. So we having a two boundary condition. First one is at node 1 and 5 the deflection is 0, and second boundary condition, deflection y2 is equal to y4. And we know the central finite difference equation is yn minus 1 minus 2 yn plus yn plus 1 is equal to h square mn divided by ein. Let us apply this equation for node 2, 3 and 4. First, let us apply the central finite difference equation to the node 2, and the value of m is moment is 18.75. Therefore n is equal to 2. Now we having this equation where we have to put n is equal to 2 now. So yn minus 1 become y1 minus 2y2, putting by n as 2, then plus this n plus 1 is here, so it become 3 y3 is equal to h square m2 divided by ei2. Now we know the boundary condition as y1 is equal to y5 is equal to 0. So here y1 term will be 0 because deflection at the simply supported end is 0. So we have minus y2 plus y3 is equal to h square m2 divided by ei2. Putting the value of h is 1.5 square and moment is 18.75 divided by e into, now I2 is 1.5I because of the varying section, is equal to, by simplifying, 28.125 divided by EI. Let's say this is our first equation. So this non-prismatic type of beam, we have to take care of a moment of inertia because it is varying. So according to that, we have to take average where it is varying. So that care we have to take. Now let consider node 3. So n is equal to 3, and apply the central finite difference equation for node 3 where the moment is 37.55. So when we considering node 3, so adjacent nodes come in picture or appeared in the equation. So this is our equation yn minus 1. Now putting n here 3, it become y2. Now minus 2 yn become y3 minus 2y3. Next is yn plus 1, it become n is 3, so it become y4 is equal to h square m3 divided by ei3. Now putting the value of h and m3, h is 1.5 and m is 37.55, and now here the moment of inertia is for I3 or for node 3 it is 2I. So putting that 2I, it become 42.24 divided by ei. So here we having a equation 2 by considering the node 3. Now let's consider next node, that one is a node 4. Now let's consider a node 4, that means n is equal to 4, we have to put and apply the central finite difference equation. So at node 4 moment is 18.75. Now the equation is yn minus 1 minus 2 yn plus 1 is equal to h square mn divided by ein. Now putting here n is equal to 4, so first term become y3 minus, now here put n is equal to 4, it become minus 2y4, then n plus 1 is there, so plus y5 is equal to h square m4 divided by ei4. Now we know that boundary condition at the end y5 is equal to 0, so this term will be 0. So we have y3 minus 2y4 is equal to Now here h means L by 4, because 4 part we divide the beam into the 4 part. So L by 4 square into moment, we know 18.75 divided by EI 4. So by putting value of L, we have 1.5 square into 18.75 divided by E into. Now here the for the node 4, the moment of inertia is average of either side, I plus 2I divided by 2, it become 1.5I. So putting here 1.5I, we have 28.12 divided by EI. So this is equation number 3, or we may take directly previous equation, one may take directly previous equation because of the symmetry. So now by considering node 2, 3, 4, we having a 3 equations. So those equations are, first one is minus 2y2 plus y3 is equal to 28.12, first one. Second is y2 minus 2y3 plus y4 is equal to 42.19 divided by EI, second one. And third one, y3 minus 2y4 is equal to 28.12 divided by EI, third one. So the we know the at end deflection is 0, y1 is equal to y5 is equal to 0, and y2 is equal to y4 due to symmetry. So we are having a two boundary condition. Putting that boundary condition here, we can solve the or one can solve the problem. Now here the one may consider this y4 in term of y3, and by putting here we have, instead of y4 we will get y3 from this equation, and by solving this 1 and 2 we will get y2 and y3. So y2 and y3 will be now here the y2 is equal to y4 is equal to minus 49.22 divided by EI because of the symmetry. This is one is y3. So y3 is equal to minus 70.32 EI. So at midspan the deflection is more as compared to the y2 and y4. Okay, so these are the value of deflection. Thank you.